the speaker is Remigiusz Augusiak from the Centrum for Theoretical Physics, which is our institute. And he will tell us about how to apply the locality for certification of quantum states and measurements. And well, this talk was given in September, the 1940 meeting of the Polish Physical Society. So the problem we consider is that, okay, we have a new, there's a whole wave of new quantum technologies. Okay? And those quantum technologies need some certification tools in order for them to be certified. So you need some mechanism to check whether these technologies work as desired, as you expect, and they produce the proper outcome. And one of the approaches for these things is the device independent certification. So in the next few slides, I'm going to explain this type of notions. Okay, so I will start from defining what device independent certification is and what self-testing is. As a particular case of device independent certification. So let me start from the standard birth scenario where we have some example of a multi-particle scenario where we have two parties, A and B. This party shares some state, AB, and they can, with their devices, they can perform measurements, okay? And in this particular case, we have two measurements at each side, like two for Alice, two for Bob. They are represented by some quantum observables here in this picture. These observables have two outcomes, plus minus one, okay? So they obtain the state, they obtain particles, they randomly choose the measurements that they want to perform, they perform the measurement, they obtain an outcome. And the correlations that they observe here are described by a collection of expectation values. Okay, in this particular scenario, you can work with these expectation values instead of probability distributions. But in general, this is not true. You have to do some tricks. And so, if you violate an inequality, then you know that you have the nonlocality. And here we have the most known example of an inequality, which is the CHSH inequality. A consists of four terms. It's a linear combination of four terms. If you observe that this value is greater than 2, then the correlations that you will produce in this setup are non-local, and this non-locality is useful. So here's a list of applications of non-locality. So you can use it for certification of certain properties, quantum properties, and the most powerful in this context is self-testing. So let me now introduce the idea of device independent certification. So we have exactly the same setup. So we have the same experiment, but now we will make any assumptions about the measurements that are being performed and about the state. And the only knowledge about the whole setup is given by the set of probability distributions or by the expectation values that I introduced before. So if you have more outcomes, you should use this picture instead of this one. This one is kind of incomplete. Okay, so now the task is given these numbers for violations of the inequality. You would like to say, being able to say something about the quantum setup, which is here. So in particular about the state and the measurements. Okay, and the definition of self-testing is the following. So I want to be able to deduce from the observed correlations that there exist locally arbitrary operations at Alice's and both sides, which transform my state, which is here, which is produced by the preparation device, which is unknown to me. Okay, so I don't know psi. I know that there is some psi, but I don't know the form of psi. So I would like to be able to say that there exist these unitary operations that bring psi to some known state that I would like to certify in my device, okay, times some auxiliary state. That's the task. And the same thing you can do for the measurement. So there is a choice of basis, local basis, such that the measurements that is being performed on Alice's share of the quantum state psi can be brought to some known measurement. Okay? Is that clear? More or less, no? And the important thing is that here this identity acts on this auxiliary state, and the same for all. So you don't get any correlations from this part of the quantum setup. Okay? The only correlation comes from here. Okay. So this is what we call a reference experiment, because this is the experiment, kind of, like the setup that you want to certify in your actual experiment. And this is called self-testing. So if you are able to deduce the existence of this local basis, so that all these things are true, then you say that you have self-tested psi prime, a prime, okay, so this is a way of certifying that your device has produced what you wanted to produce, right?
So one question, like you limited yourself to observables earlier and correlations. So I guess it's meaningful to ask about self-testing of correlation,
Measurements.
Sorry, like okay, how it doesn't make sense.
Well, I mean,
like, so like in general, just correlations or those expectation values, they don't. It's not just. Okay, you get more than just correlations, right? So you like in some cases it's possible to self-test, sorry, from correlations alone.
Yes.
Sometimes.
Yes, it's okay. In general, it's better to use correlations because they give you more information.
Okay.
Violation probability quality is just one number. I mean, it's like the bell value is one number, but here we can have more. And there are papers that kind of challenge certification based on locality. Of course, if you are able to make this type of statements, it means that you have observed the locality. I mean that this correlations are very local. Without this, you wouldn't be able to make the statements. Okay, this is for sure. But I agree. As like it's kind of so maybe easier to work with violation of value quality, because if I violate a value quality, I know that this violation would be useful. If I observe some violation, I don't know whether it's local or not. So, but maybe it's a matter of choice. Maybe I prefer to work with locality or like maybe violations, but some people prefer to use this numbers, all of them at once.
Yes.
Uh-huh.
This side is bipartite.
Okay, so here, because it was the meeting of the Polish Physical Society, I wanted to make it simpler, but this extends to the multi-party case. And provided, I think, in terms of multi-party studies and so on. So you will have like a local choice of a basis for Alice, Bob, Charlie, and so on. And people do this, and the people study these kind of questions for the multi-party scenario as well.
So just very naively, like if some Bob certified they have a maximum entangled state, then they're confident there's no entangled elements. So kind of
Yes, and this type of thinking, maybe so this type of thing was already somehow proposed here, because the reason why Arthur Eckert added violation state SH in his paper was exactly this. If you maximally violate, you know that you have the maximally entangled state between Alice and Bob, which means that it's uncorrelated to the use of operation. Okay, so here comes an example, the simplest one, which is one based on the maximal violation of the CTP value quality. Okay, if you observe the maximal quantum value, which is 2 square root of 2, by some state in some observables, then you can prove that this state under some local unit operations can be brought to the maximally entangled state times some auxiliary state, and the same for the observables. Okay, this would be like Alice's observables would be X and Z bounding matrices. Now it's your problem. And for both, these are combination problems. Okay.
You have to click. Oh no, it works.
Okay. So this idea seems very attractive for the community, and many results have been proposed in this direction. So, for instance, this paper shows how to certify any pure bipartite entangled state of the local dimension. This one proposes a certification scheme for any multi-party entangled state based on quantum networks. This one does the same, but without networks. It's just direct burst scenario. Okay, so we observe some violation of the inequalities, and we are able to do self-testing. And the same was for the measurements. So that the other slide was for the entangled states. This one is for measurements. So this is a paper published quite recently in Nature Physics that shows how to self-test all real projective measurements. Real because there is this problem of being able to distinguish between a state or a measurement in its complex configuration. Okay, so they directly admit in the title that they are not able to distinguish. Okay, but like no one is able to distinguish. Some people admit, some not.
So actually, your like slides like two slides ago, like you didn't admit this.
No, because in this particular case, there is no problem.
For features.
Because it's real, you see the state is real and the measurements are real.
Okay.
That's why this particular case is nice, but if you go for some, so for instance, if you have all pure bipartite entangled states, there's no problem because you have the Schmidt decomposition. Okay. But if you go to the multipartite scenario, there is no problem, and also for the measurements. So if you have arbitrary projective measurements, you cannot always bring them to real projective measurements, right? That was a paper showing how to self-test entangled measurements in quantum networks, and this was a paper in the prepare and measure scenario, which shows you how to self-test arbitrary measurements. That scenario. So this scenario is different from the first scenario because here we have to assume the dimension of the particle that is Centrum minus 2 power. Okay, so there is some additional constraint that helps to derive results. Okay, the question we wanted to study here. There were actually two questions we wanted to. Well, there was one question that we started from, which is how to self-test an arbitrary measurement. And then this question extended to the other question, which should be on how to self-test a mixed state. Okay. So in general, if you have the first scenario, you can self-test a mixed state because if you observe maximal quantum violation of an inequality, it can always be realized with a pure state. So you will not be able to self-test a mixed state. Okay. If you have a mixed state, you will also not observe the maximum quantum value unless you have particular inequalities which are violated by equal subspaces of your sets. Okay. Yes, so that was the initial question. Okay.
So by arbitrary you mean non-projective or
non-projective and also composite. So
okay.
So we try to extend in a way this work. Okay. So we not only want to certify measurements that act on a particular Hilbert space, but also those that act on multipartite Hilbert spaces, which are entangled, and we want to go beyond the projective measurements. So when we were working on this paper appeared before us, but we already had part of our results. Okay, so there was some kind of competition, let's say. In any case, it was I think we sent our paper to the same journal, and I think it would be much more successful if this paper didn't get published before we finished our paper. Okay? So now people can say, look, this is just an extension or whatever.
Can I ask about the philosophy, I guess, slightly? When you're self-testing measurements, do you trust the states, or do you also like
No. So
take them away?
Well, this depends on the scenario you want to consider, but in general, if you work with nonlocality, you don't trust anything.
Okay.
So you certify both.
Yeah.
But usually the papers were written in the following way. So people have found methods for self-testing entangled states, but by the way, they needed also to self-test the measurements because this is always how it goes. Okay. But there were no papers about general methods about measurements. There were general papers about entangled states. So then we started to work on measurements. Okay, we wanted to change the narrative and find general results for measurements. But then they were faster. And also them. Okay, so these are the papers that that I want to present, but in the end I will present what is in this paper. So this is a paper that we wrote in 2023 as well, I think. And here the idea was that we take the simplest network that allows us to suppress measurements coming from unextended product bases. And this was only because Saronat, me, and Chayam were interested in unextended product bases for other reasons. But then we realized that perhaps we could also try to suppress them in quantum networks. Okay, here is a slide about quantum measurements. This is like for general body. Maybe I skip it because I guess you know it. The important thing is that quantum measurements form a complex set, okay, and they have extremal elements. And extremal elements, like extremal measurements, are those that can be written as a complex combination of two other measurements. Okay. And we will use that later, okay? This part that we have extremal PMs. Okay, so this is the scenario that we consider. We have a star network, which doesn't look like a star, but we can the drawing represent as a star. So you have a central node, E, and you have n auxiliary parties, denoted by A. And the auxiliary parties perform, each of them performs 3 measurements, 3 binary measurements with 2 outcomes, and then you have a central party with 2 measurements. One measurement is going to be a measurement in the GEZ basis, so that we first have to certify it, okay, so we don't assume it. But this
What is GEZ basis?
Well, you take the GEZ state, you put minus, you have another one, and then you split the bits, and this way you can generate the basis, right?
Okay.
It's like 0, 0, 0 plus minus 1, 0, 0, 1 plus minus
Like it's
1,
2
0.
it's 2 qubits.
The one I told you is 3 qubit. No, but here it's like in qubit.
Okay,
basis.
okay. Gotcha.
Okay, and here you have the second one is the one that you want to certify. And then we have this correlation we observe in the whole. And it's like I forgot to say, here we also have n sources of particles, and these sources are assumed to be independent. So there are no correlations between them. Okay? So each source sends one particle to E and one to one of the A particles. Okay, so they perform the Bell experiment, they observe some correlations. Okay, and now, so the first thing is that we choose this first measurement by Eve. And for the correlation generated for this first measurement, we check violation of a number of inequalities. Okay? If we observe maximal violation, then we are able to prove that all sources generate the maximally independent state. So we have n sources.
So I'm confused because like this Eve performs some collective measurements on this many days, and we can still have some kind of Bell inequalities.
Yes.
There, but like it's for the network scenario, those inequalities for.
Yes. So the you see, you have only Alice's measurements. So these are the correlations that are.
Okay. Okay.
Look, in the ideal setup, if you have the maximum independent state, if performs this measurement, she generates the GEZ state among the parties here.
Okay.
So we took Bell inequalities that are maximally violated by the GEZ states. Okay.
I see. So this is something like conditioned on some outcome.
Yes, it's on the equal 0.
So
for
I
each-
see. I see. Okay. So it's like.
So for each different outcome of Eve's measurement, we have a different inequality.
Okay, because like initially those things are separable across the analysis, but then implementation of the specific basis.
But now I think maybe this can be simplified actually. Maybe you don't need so many inequalities. Because in the end, maybe you need to generate non-GEZ. So like you have a 2-outcome measurement.
Yeah.
So one outcome corresponds to the GEZ state, and then the other
Some
one.
specific GEZ state.
Yes, exactly. And then you test everything on this GEZ state, and then you can still prove that the states are maximally.
Okay.
So that was a good question.
Eve has two measurement inputs.
Hmm?
Eve has two measurement inputs. So,
Yes.
what are these two?
So one is the one that we use for testing the whole setup, which
It's also G.
is, yeah, exactly. So in the ideal case, it's like a GZ measurement. It's like a measurement in the GZ basis. It's like a kind of measurement one. And one is the one that you want to certify. But everything is unknown at this moment, okay? So we know that the ideal setup, we like to have here the GZ measurement, the maximal entangled states, and Pauli matrices here, okay? But we don't know this thing. So first, we use this first measurement to certify everything. Once we do it, then we can use the second one. But it's not that like we ask if to keep picking zero. I mean, they can independently choose whatever they want. We collect the statistics, and then we choose the part of the statistics corresponding to equal zero. Okay. Based on that, we are able to say something about the network. Once we characterize the network, we can also say something about the measurement that we wanted to certify. Okay. Okay. So if this inequalities are maximally violated, you can certify, you can prove that those states are equivalent to the maximum of the state. Okay. Times, of course, something else which we don't care about. And then you can also prove that all the local measurements are x, z, y, or minus y. And minus y is because of the complex conjugation problem. So you can distinguish between the two. So you can consider that you have y or minus y. But usually we pack it in one observable. We just write y times some other observable, which is eigenvalues plus minus. So you have like y on one substrate and minus one y on the other substrate. Okay, so you are able to, so from this simple experiment, you are able to certify all the sources and all the measurements here. And now so the thing that we kind of were heading to is what was used in the paper by Remigiusz and collaborators, which was also published in Nature Physics. Is that if you have a complete set of tomographically complete set of measurements, now we can kind of characterize every measurement here. Because if you perform a measurement on those particles which are here, then you kind of teleport them here. And when Alice is performed their measurements, they do the tomography, device independent tomography. Okay? That was the idea.
But a silly question, is this y or minus y, that is a problem then? For tomography?
No. No, here no. So in this case, it's not a problem.
Because just conceptually, you said that, okay, you kind of self-test those measurements on other sides, but then you are not certain, like, whether it's y or minus y.
Well, it's a problem in this sense, okay? So we either have the measurement or it's
Okay, and it might then like also it might be for R. Okay, so it's for R, it's gonna be also a problem. Like this,
yes,
testing
like,
is
yes.
okay to propagate.
Yes.
Okay.
But we accept that. That means like
Sure.
there's no, well, maybe there is, but recently we found that there are other symmetries here. It should also be included in the definition of self-testing. So it seems that the only problem is complex conjugation, but there can be also partial complex conjugation. Okay? Which poses a question whether this definition for use is the most general one. Actually, it makes sense to still work on this kind of questions. Okay, so now we assume that the second if measurement is an extremal measurement. This can be a projective measurement or some other PRBM which is extremal. And this is what we want to prove. That there exists a unitary operation on the if side, which brings the measurement operators to a given measurement operators times identity. And because of what I said, that you can do this local quantum tomography device dependent way, let's say, what we can prove is that you either have the measurement itself or its complex conjugation. Okay? Well, and then, so this is like, this is like the same, but this is like for the composite measurements, because we have composite Hilbert space, the underlying Hilbert space is a composite one. But then we can generalize to actually any measurement, but we have to be able to embed it in a measurement which acts in a composite Hilbert space. Okay? So that will be a part of measurement that we also certify, plus something else that completes the whole thing to the measurement in the huge Hilbert space. Well, then we noticed that this was actually noticed by one of the referees. We submitted the paper to Nature Physics. One referee was okay, but maybe this referee poses and notice that look, if you can certify any external measurements, you can also certify complex combinations of them. Okay. But this was a very simple omission. We added this to the paper now. So now if needs to have many buttons, one corresponds to the genes-based measurement, which was the one used for certification of the whole network, and then we can have many measurements that are external, okay? But we have to press the buttons with some probabilities, and in this way we can characterize the element.
But okay, can I ask, so like if you don't have those buttons for different measurements, but the measurement is not X3,
No, then we use externality in the tool.
but just naively, okay, because you probably you have some sort of Bell expression for that, right? I guess, but
No, this one we don't have, we just have the tomography.
okay, but quantum tomography you can do also for you can realize all imperfect measurements.
Yes.
Right?
Yeah, so if you have if you have fixed dimension and you don't have this auxiliary path, then this is true. You can fully characterize the any operator, right? You have the but because we have this additional thing, we have to assume that the measurement is extremal. Well, maybe
I see. So, but then do you think that this is like fundamental that you cannot do with, or it's
okay? To be honest, we used it and we're happy that we proved.
yes.
And then we stopped thinking whether we can relax.
Sure.
But there is this other paper about certification of maximal randomness from 2-qubit maximal random state and for outcome POPM on one of the sites, and they also use this externality there, and I think it's and they do exactly the same thing. They do this. I mean, they do this device-dependent tomography, let's say. And I think that as far as I remember from the proof, it's essential to assume externality. Otherwise, you won't be able to fully characterize the measurement because there is this additional part. Which
so you imagine one can look up some counter examples.
Yes.
Okay.
Can I ask, so we have this on this slide. So I'm looking at this GHD basis measurement that Eve does, and I'm kind of trying to understand what goes wrong if when you press about 0, Eve just tries to break it down inequality with each other separately. Does this also work?
What do you mean that Eve tries to?
So when you press 0, okay, no.
But here it's like they don't want to cheat. I mean,
Yeah.
I assume that they want to cheat each other, but they don't want. So in this scenario, they collaborate.
Okay, yeah.
They want to.
These are trusted parties.
Yeah, so like
trusted in the sense that they don't conspire against each other.
Yeah.
But they are trusted in the sense that they don't know what measurements they do.
Okay, it makes sense. Actually, no, I'm serious. Okay, so.
Okay, and then you can also certify mixed states in this way, because if you have a pure state, you have to you can design a measurement, okay, for which one of the outcomes is represented by the projection of the pure state. So you do the full tomography of that state, which is exactly very similar to the scheme by Ivan Šupić. If you have mixed states, you design a measurement which has this measurement outcomes, measurement operators. Okay? And then you have to again complete it to an external measurement. And in this way, you can certify the state. So mixed.
So you start with eigen composition, bro.
Yes. No, this can be in the composition.
So you mean that you would, I mean, okay, that this MK will not be external automatic. Well, you cannot.
Yes, so exactly, you have to add some measurement operators to make it extreme.
Okay, but like imagine that you have some redundancy there, like in like you put like twice, like formally twice zero state. Okay, okay. So some of those operators can be like if those psi k's as projectors are not linearly independent, then your measurement.
Okay, you're good. So I take the eigen position. They are from
Okay.
So the new feature here is that this is impossible in the standard scenario. Okay, these are the open problems. Maybe the robustness to if you don't observe the maximum quantum value, but the maximum quantum value is some epsilon, and what happens then you would expect this type of results. So there is a map that one acts on your measurement operators. And the distance between the reference measurement operators, what you have in the experiment under some map, is bounded by a function that depends on epsilon in such a way that if epsilon goes to 0, this function also goes to 0. So we have some statements like this, but for this type of networks, it's really difficult to prove anything of the sort. So we usually provide results, like exact results, and then we hope that they're very. Maybe I shouldn't say this thing.
Because they're very.
Recently they're less happy.
Okay.
Okay, make the schemes more practical, so lower the number of measurements, because here, as you can see, the number of measurements is huge. You have to check a lot of inequalities. And the thing I would like to explore now is to relax this assumption that the source is independent. So you have to prove that the source is independent from the other source first, before you start the certification thing, which will make the scheme even more complicated. But okay, it's like proof of principle. So we wanted to show that it's possible. Okay? We are happy that it's not something that you can really use in the lab, right?
So can I
I
ask?
have more slides, I guess, but
We are good with time, you know.
no, but let's. We'll have meetings for 2 hours. And this is the team. So Ryan was my PhD student, and this is the picture taken after he obtained his PhD at our council. This was my postdoc. Augusiak is now at the Institute of Basic Problems of Technology, Science. Well, it's another institute of Polish Academy of Sciences. Also, Sarah was my group till August, and then he left because he got a position. Chandler was a postdoc of Alexander Streltsov at the University of Warsaw. He also left, and Gautam was my postdoc, and he also left. But like the paper that I presented is between me, Ryan, and Alexander. Ryan was I'm really happy with him. So he became very smart and creative. Okay, this is the announcement of the new group position. Okay, maybe I skip this.
Okay.
Okay, thank you.
Okay. You have the chair, right?
What do you mean by general? Please skip to the previous slide. What do you mean by general quantum map? How do you imagine what could we certify in this scenario, for instance?
Well, imagine we have a map acting on those states. For instance, one particle goes to A1, A2, and so on, the source set, and then you apply a quantum channel.
Because in particular, measurement, for instance, is a class of quantum maps. So you just go to beyond this.
Yes, not go beyond this.
So
like Ryan already did that for unitary operations because he wanted to find a scheme certifying any quantum value. So he extended this.
So he has a paper.
He has a paper on it recently, and the question is, well, I think it's doable, and it's like if instead of a measurement, you have a map, you can also do this. But someone has to see it and do the calculations. Maybe
So is the idea basically, because you can certify measurement, you can certify states, and you have different rounds, and
Yes.
then you can, if you have trusted measurement, you can sort of, in some round, when you are allowed to press some buttons, you can do it effectively tomography of this.
Yeah, so it's
measurement.
the same. So first you certify the whole thing, so you know that you have
Yeah.
maximum state, and then you press a button and you apply the channel.
Okay, okay.
And then the channel applies to half of all the maximum states.
I see.
If you apply the channel to half of the maximum states, you get another quantum state, right?
Sure, sure,
You
sure.
can do the quantum tomography of the state.
Yeah.
So this boils down to certification of a quantum state at the end, because
Yes.
action of a quantum channel produces quantum state. So
Yes. Maybe you also do that.
Question about the bad inequality or so what assumptions goes into the classical modeling of it? I suppose it's between classical and
Yeah.
this bound is classical bound, right?
Yes.
So what are the assumptions for the model? So is it local?
You mean to derive those inequalities?
Yeah.
Yeah, so we have, so these are inequalities under default locality model. So,
Okay, so it's a model.
so
Yeah, I'm curious how to deal with the multi-party scenario.
So here we take the simplest model. So if we violate this inequality, it means that there is some locality in the system, but it's not genuine locality.
Yeah.
Do you want a formula? I can show you the formula. The model.
Yeah, it's maybe later. Yeah, now.
So you have this probability distributions. And it's like a fully separate object. There is no locality inside. But actually, we are trying now to work with this before this text and to take genuine locality. Okay, let's take the speaker again.